Okay, let's go ahead and get started. First of all, welcome everyone to today's webinar. The goal of this session is to help new users become familiar with design of experiment concepts and to introduce Stati's design expert software uh, for the creation and analysis of multiple types of experiments. By way of personal introduction, my name is Richard Williams, and I've been a Stati's consultant for a few years now. But prior to that, I spent 38 years in the chemical industry, often in roles focused on product and process development and improvement. By training, I'm a chemical engineer with a business degree. And over the years, I've developed a bit of a passion for design of experiments. I personally feel that the tool has been underutilized for problem solving and process optimization. But equally, I think DOE is extremely helpful for problem prevention. And by that, I mean quality by design. The idea that DOE can help us launch reliable products and processes from the very start. Over the past 10 plus years, I focused on providing training for product and process improvement tools. So today, I'm very happy to provide this webinar to get you started with design of experiments. A bit of a warning though, this is a huge topic and we'll only be able to scratch the surface today with a 1-hour webinar. But at the end of this presentation, we'll give you resources to continue your DOE journey as we move along. Okay, so welcome. Let's go through a little bit of housekeeping. First of all, to prevent audio disruptions, all attendees are going to be in mute mode. So that'll keep things a little bit quiet. We have 41 people out there, and if we open up the mics, I think we'll have a little background noise. So we'll try to keep that calm. If you do have questions, I have two options for you right now. First of all, within the GoToWebinar tool, there is a box for questions, and that is being monitored. So if you do have especially a quick question or a clarification that you'd like answered, feel free to move into the question box, and Sherry Kraber, who is on the line, will be happy to address those. You can also send questions to stathelp@statis.com. And if you do, please provide your company name, and if you're using Design Expert, the serial number for your software. You'll also find the slides that I'll be using posted in the handouts section. So if you go down in the tool, you'll see a handouts, and there's one handout that's available. So you can have access to the slides that way. Also, tomorrow, you'll receive a link to the recorded webinar that we're going through today. So that's all out there. So my primary goals today is number one, why should we consider design of experiment methods? Why get into this at all? We're also going to get into demonstrations of three different, vastly different types of designs. I want to give you a very broad perspective of where DOE can apply, and then give you the opportunity to deep dive into the places where it'll be most relevant to you. So I want to give you an awareness of applications and design types, and like I said, next steps of how to get further help. Now, just to make sure that we're all here and hearing what's going on, if you would go into the tool, there's a little raise hand feature. And if you would click on that, just so that I can see who's able to hear the presentation, I would appreciate it. Okay, I'm seeing a few hands raised. Excellent. Okay, good. So apparently it's coming through. Very good, thank you. While we're there, how about another show of hands for who's working off-site today? Who's working from home or some other remote location? Yeah, a lot of us. Me too. Okay, excellent. So we're taking advantage of this work from home time here today, and that's hopefully a good thing. All right. So the agenda, I want to go through what's in it for me. Why think about design of experiments at all? We're going to get into three different case studies. We're going to look at a factorial design where we're going to characterize the vital interactions and look at the main effects. We're also going to do a response surface design which will be a little bit more of an elaborate design compared to a factorial, and we'll see when and why that applies. Then we're going to switch gears completely, and we're going to move over to mixture designs and have a peek at what that's all about and why they're different than factorial or response surface methods. And we're going to use an optimal custom to look at a fairly complicated design that looks at mixture or formulation as well as a process factor, which would be the amount of the formulation used. So we're going to get into three very different designs to kind of show you the versatility of these tools. So what's in it for me? Well, first of all, what exactly is a designed experiment? And here's one way to describe it. It's a planned approach for determining cause and effect relationships, right? So if we look at this thing on the right, like a process, we have controllable factors. We call those the X's, the knobs that we turn on the machine. And then we have these responses, things that we're interested in, called the Y's, okay? And our job is to try to find the relationship between the X's and Y's. For example, we might be interested in how to control the propagation of the coronavirus, and the controllable factors might be things like social distancing or wearing a face mask, okay? But we also have noise factors, the Z factors, which are there to confuse the relationship between the controllable factors and the responses. You know, noise factors for the coronavirus might be we have a certain segment of the population that's immune to the disease, so it's difficult to relate the controllable factors to the responses, or perhaps the test method itself is not terribly precise, and so we're getting a little noise from the measurement system. So our goal in any experiment, but certainly design of experiments, is to relate the X's and the Y's in the presence of the noise factors, okay? So despite the noise factors, we still want to come up with a correlation between the X's and the Y's. Now, one of the unique features of a design experiment is that we can identify factor interactions. Well, what's that all about? Well, factor interactions are when the impact of one factor depends upon the set point of another factor. If we look at the little graphic on the right, this is a fictitious example, but this is looking at perhaps the impact of social distancing and wearing a mask on the spread of the disease. Here we're looking at the case, how long it takes to double the number of cases, okay, the cumulative number of cases. Again, this is a fictitious example, but this more or less is the theory. If we have high social distance, so we're not near each other, the impact of wearing a mask, so the blue line is no mask, the red line is with a mask. The impact of wearing a mask at high social distancing might not be very strong, okay? On the other hand, if we're not socially distant, so the social distance compliance is low, then the impact of wearing a mask might be very, very high, okay? There's an interaction taking place. So the impact of one factor, say the mask, depends on the set point of another factor, the social distance compliance. So the idea here is that one factor at a time experimentation, where you just look at mask or you just look at social distance, you can't identify these interactions. Only using a DOE can you do that. So the second bullet point, multi-factor experimentation by its parallel processing provides more information in fewer runs than one factor at a time. And the statistics that go along with design of experiments provides confidence in our findings. So there's a lot to it. Now we have a full array of design types and analysis tools to address three overarching goals. One reason we could do a design experiment is to screen. We may have 20 different factors that we think could impact a process, and we want to reduce that down to the critical 3, 4, 5, the relevant few. Once we have that, we may want to go ahead and characterize the critical interactions so we more fully understand the system, right? So there's two levels of experiments that we could conduct. And then we ultimately may want to find the optimal conditions for peak performance. That might be a response surface design potentially. So the little graphic in the upper right shows in the software the different kinds of designs that would be available to us. We could have factorial designs where we look at the impact of factors and the interactions. Response surface, where we are actually going to create a predictive model. Mixture designs, which is the same thing but is tailor fit to the formulation or mixture environment. And then custom designs where you can do all sorts of different things, very flexible. So let's begin by looking at a factorial demo characterizing the vital interactions. So just briefly, here's kind of the recipe for an experimental plan, what we need to run through in order to do an experiment. I mean, obviously, the first thing we need to do is define our objective in terms of a measurable response. We need to define the whys that we're interested in evaluating. Then we need to look at the input factors to study. Those would be the X's. Then we need to select the design. Okay, this is where the software can help you choose along with the study that you put into it to understand the options that are available. The hard part, of course, is conducting the experiment. That's something we probably can't do for you. But once you do, then we can jump back in at step 6, which is to analyze the results using the statistical tools baked in the software. We then want to look to make sure that there's no odd occurrences taking place in the data itself or the model fit, and we will diagnose the residuals, looking for outliers, etc. So we'll take a peek at that. Then we like to use graphical methods, so we're going to look at the outcomes, the impact between the X's and the Y's using model graphs. Then we can go ahead and optimize the system. We always like to come back in and use some confirmation runs to verify that we in fact have defined the proper optimum and made the proper connections. We always like to celebrate at the end, so we'll throw that in there too. Here's our first example. So again, I'm a chemical engineer, so I have a couple of these that are going to be a little bit more related to that environment, but hopefully you can relate to the designs that we're talking about. Here, what we're trying to do is maximize the yield of a chemical reaction. And the engineers say that there are 5 factors that they believe could have an impact. We're going to have the feed rate, catalyst, agitation, temperature. The last one is going to be atmosphere, which could either be nitrogen or air inside of the reactor, right? It's going to cost us money if we have to use an inert nitrogen atmosphere, so we'd rather do it in air, but that may have a degradative effect on the yield, so we want to take a look at that as well. So the goal is to maximize the yield. The one thing that we want to do is we want to make sure that we are collecting enough data to answer the fundamental question. We want to check for power of the design. So in order to do that, there's a couple of inputs. We want to take a look at the delta Y. Now, this can be a little bit nebulous, but what it boils down to is this. Any improvement less than the value we pick, in this case, we're picking 3%, any value less than that will be unimportant, and we're going to set up our experiment so that we might not catch things that are less than 3 percentage points change in yield for this design. And we're going to be okay with that because it won't be important. That our goals would be that we want to increase yield greater than 3%. So we're only interested in the things that contribute by at least that much. And we're willing to miss or forego identifying things that are less than that. The noise, the standard deviation, we're saying is 2%. And that's the variability in the reaction, sampling, and testing. And well, where does such a thing come from? Well, ideally, if we have some production data or we've done other DOEs in the past, we're going to have an idea of the standard deviation of the system. If we repeat the same experiment, 10 times, for example, and we calculated the standard deviation, that's essentially what we're trying to put in here. It's just the idea of how much noise or natural variation exists in the system. Okay. All right, so let's begin by taking a look at the software. And when we open up the software, this is the opening screen that we would typically see, right? This is Design Expert, Statis Design Expert version 12. And we're going to create a new design. So we will click the button that says New Design, and we'll get this splash screen. So this is where it takes us at the onset. It brings us into, well, let's take a look at this left-hand panel to start with. Here we have the different design types that are available to us. Okay, we see factorial designs. Here we see the regular two-level factorial designs that are highlighted. It's highlighted to that because that's probably the most common, but by no means the only type of design that's used. We also have response surface, mixture, and then custom designs further on down the screen. In this factorial randomized regular two-level design, we have this table that shows the number of factors along the top. In our study, we have 5 factors. And then there are different designs that can be selected. If we do a full factorial, where every factor is evaluated at every combination of the other factors, it'll be a 32 run design, a full factorial, okay, 2 to the 5th. So that's what we're going to pick in this particular case because it is a full factorial design. But notice that there are some other designs above it, a green one and a red one, that would use fewer runs. For example, we could do this experiment in 16 runs, and that would be a green design, which, to cut the story short, a green design is generally a good design in that it will at least identify the main effects and 2-factor interactions. So we could pick that one if we wanted to, but we won't in this particular case because we are going to do the full factorial example. So we're going to pick this one. Then we will hit next. And this is where we're going to input our factors and the information that we want. So we would type in feed rate, etc. We will put the low level that we're studying and the high level that we're studying, right? And we want to set those levels far enough apart so that we expect to see a substantial change in our response. We don't want to be radically crazy wide with it, but we don't want it so narrow that we wouldn't expect to see a significant change. So we would go ahead and we would tab through and put all the information in. Notice that the last one, atmosphere, is a categoric variable. We have an option to choose numeric or categoric. That one's categoric because it's either nitrogen or air, right? So we can use that type of factor as well as numeric factors. We will hit next. Now we want to evaluate to see if we have enough power to find what we're looking for. Are we doing enough work, enough runs in the experiment? Now, if you remember the difference to detect, the delta Y, we said that was going to be 3, and that the standard deviation was going to be 2. So the signal to noise ratio is 1.5, 3 divided by 2. And now when we hit next, we get a power of 98% to find all the main effects. And that is a very, very high number. We at least want to see 80% there ideally. Going over 95 is oftentimes a little bit too much, but this is certainly a well-designed experiment to find what we're looking for. So we will go ahead and hit finish. Okay, so here's the experiment, our 32 run experiment. Notice that the runs are randomized, that there's a random order to them. And that's a very important aspect of DOE. That can help protect against a lot of problems, and we highly encourage randomization of the runs when we execute the DOE. Now we need data, and in this case, it'll be a little easier because we are going to run a simulator to get our data. This one's going to be called Reactor, and we have data. Admittedly, a little bit easier than it will be for you. Once we go through this, on the left-hand side, as we work our way from top down, our design actual is up here at the top. Under analysis, we will now come back in and we need to click on yield, and we need to go through some steps to analyze this data. We're going to go left to right on the tabs. Transformation is usually one that we just leave alone until we get an indicator that we might need to do that. Let me just briefly mention that a transformation is when we do a mathematical operation on our response data before we analyze it. For example, we may take the log of the data before analyzing it, but we'll see where that comes into play later. Now we will hit the effects, and this is where we have a couple of graphs that help us pick what belongs in the model. Now, what do I mean by that? Well, we're trying to find out what factors and interaction terms actually govern the relationship between the x's and the y's. And the way this works is this red line represents the z factors, the noise factors, and everything that isn't on the line is a relevant factor. So I'm going to select all of those. And notice on the right-hand graph, the Pareto chart, we see that these same bars, these selected items now tower above the statistical tests that are there, the Bonferroni and the t-value limits. Okay, so we've made a pretty good selection here. And look, if you carefully can see that we have factor B, the catalyst, we have D, temperature, and E, atmosphere, but we also have two-factor interactions that seem to be highly relevant to the system. One factor at a time experimentation would not have found that. Once we've picked what belongs in the model, we will look at the analysis of variance table, the ANOVA table. And here, we have a few details that we're going to briefly go through. Well, the first thing we want to know is the model we selected statistically significant? Well, the easiest way to see it is it tells us the model is significant. But what it's looking at really are these p-values. And with 95% confidence, we're looking for a p-value that's less than 0.05. So any p-value less than 0.5 is statistically significant. So the model overall is significant, as are the individual terms that we've chosen from the previous slide to be in the model. Okay, so we have B, D, and E, and then two-factor interactions that are involved. We also have some fit statistics. We have the standard deviation. We have the raw R-squared values, and then we also have a couple of special R-squared values, the adjusted and predicted. We spend more time focused on that. And then we also have the adequate precision, which we want to be greater than 4. If you want to know what you're trying to see on this little fit statistic table, there's a little annotation that describes really what the most important information is. So it's kind of there to help walk you through it. Okay. All right, then what we need to do is look at the diagnostics to make sure that we don't have anything really odd going on with our data. Once we've selected our relevant factors and extracted the signal from our data, we want to make sure that the residuals, the difference between the actual and predicted, what was predicted from our model, that those residuals are normally distributed. If they fall along this red line in this upper left graph, which they do, then we will consider that to have met that test. In the upper right, we have the residuals versus predicted table. And this one, we want to make sure that as we go along the predicted Y value responses that go in this case from 40 to 100, we want to make sure that we don't have a big megaphone taking place here, where we're able to make good predictions at the low end, but not so good predictions at the upper end. So there's in this case, it looks really good. I mentioned transformation. In the bottom left, the Box-Cox plot will give us a hint whether or not we need to do a transformation. In this case, it says none, so that's what we would do. We're happy with what it, now if it did make a recommendation, say a log or something like that, we would come all the way back up to this tab, the transformation tab, and pick the relevant transformation and go through the exercise again. But in this case, we don't need to be thinking about that. We also want to look at the predicted versus actual. And here we want to make sure that this line more or less splits the data along the range, that we're not over predicting and under predicting in certain ranges. And this looks good. So we're happy. Then we would go to the model graphics. In here, Design Expert picks the most relevant graph to present to you, which is an interaction plot. In here, we're looking at catalyst plotted along the bottom and temperature is the second X. And here we see that the red line is 180 degrees and the black line is 140. So the highest yield is going to be at a catalyst of 2 with the temperature at 180. However, let's take a look on this left-hand side, take a look at a couple things. Feed rate was not in the model, so I can change that and it has no impact because it's not part of my predictive model. Same with agitation. That turned out to be not statistically significant. We did notice an impact from factor E, the atmosphere, and that one is a categoric, so I can toggle that one between the two. So I can go from nitrogen to air, and if I do, we can see that that actually degrades the yield performance quite a bit. So clearly the optimal will involve nitrogen, high catalyst, the high temperature, and if I click on that to do what's called a pairwise comparison, you can see that that is statistically different than any of the other conditions because these bars do not go over that red line. And also, we get a predicted value of 93.6. So that's one way to just use the graphics to find the optimal condition. Okay. All right. So in summary then, things to remember from this factorial design. Full factorials test all possible combinations of the factors. They characterize all effects and all of the interaction terms. So not only two-factor interaction terms, but if I have 5 factors, it'll go through 3-factor interactions, 4 and 5-factor interactions. Power assesses, which by the way, those higher level interactions are highly unlikely, extremely rare. So oftentimes we satisfy ourselves by looking at main effects and only 2-factor interactions. The power assesses the probability of an experimental design to identify the important effects, and it's driven by the delta Y, the signal to noise ratio, and we typically want a power of between 80 and 95% to balance the number of runs with the possibility of against the possibility of missing something. Now, in this case, we may want to consider time and resources by using a fractional factorial. Instead of a 32 run, perhaps we could cut it in half and use the 16 run, which would, in fact, probably would have been my choice if I were actually doing that. However, instead of a 98% power, we would have only a 77% power, which is just a little less than the ideal that we would want of 80%. But we could do that experiment, and it would probably be quite helpful in this particular case. So we could get the same results probably with half the work. Okay. All right, so before continuing, let's just have a show of hands just to make sure that we're all tracking. We're still there. Excellent. Okay. Excellent. Okay, thank you. Now we're going to go into a response surface design. So a little bit more power to figure the story out, a little bit more runs. So let's evaluate how this works. So on the graph on the left, I've got 2 factors, x1 and x2 plotted, and the vertical axis is the response. And so this contour is the response surface that we create by using a 2-factor interaction model. Now what we notice is with a 2-factor interaction model, all we're really doing is putting a twist in the plane, okay? We cannot create a hill or a valley in the response surface. All we can do is put a twist to the plane, okay? So we have main effects and we have 2-factor interactions here. If we think that in the interior of our design space that there will be curvature to our response, another way to say that is we think the optimal conditions might reside somewhere in the interior of the design space, we may need to go up to a more sophisticated design than simply a factorial design. We might need to include some square terms or even higher order than that in order to fit the response surface. So that's where our SM response surface tools come into play. This little graphic on this slide on the top is a picture of a central composite design. The cube represents the factorial design points. The red represents center points that we'll put into the design. Okay, so that's something we didn't have in the last example. And then the star points are going to be, they're called axial points, and what those will do is those will help us fit the pure quadratic terms. Okay, so we're going to build this thing up a little bit more completely. Now we're going to try to work on a reaction. And we have three. We want to improve conversion and then also keep this property called activity within a certain target range. Now we have three factors: time, temperature, and catalyst. And that's kind of common. The last experiment, we had 5 factors that we wanted to evaluate for a factorial design, maybe even think of it as a screening design. But now that we've reduced the number of factors, now we want to study them more carefully, do a little bit more of a deep dive, and that's where response surface can come into play. So we're going to optimize within these 3 to address 2 different responses. So our goal is we want to achieve at least 80% conversion and maintain an activity between 60 and 66. Okay, so kind of restating then, maximize conversion and target activity. Those are our 2 responses, and then we have these goals. So let's fire up this one. Now here we're going past the factorial. We're into the response surface module now. We're working with a central composite. These are probably the most commonly used response surface designs, although a box Benken is not unusual. And if you have something a little bit exotic, we also have optimal or custom designs that can be used. But let's start here with a central composite. The number of factors, we've picked 3, that's what we have. And here we're going to do the same thing we did before. We'll input the factors and the high and the low levels. These alpha values, now that's where those axial points are going to be placed. So it will put them a little bit outside the box, the factorial box. If we need to bring those back in, we have a tool that you could do that in the options, but that's a little bit beyond the scope of what we're going to talk about today. This is a 20 run design. So we're going to accept all the defaults and go ahead and hit next. And this is where we're going to put conversion and activity, our 2 responses. Then we will hit finish and create the design. So here we have the 20 run design that we just talked about. And we get data. There we go. Now we have 2 responses to analyze, so we have to do them one at a time. So let's start with conversion. And now, because it's an RSM and not a factorial, we will have a couple of different tools that we're going to use. Instead of trying to find the factors of relevance, what we're trying to do is find the model that best fits the data. And it is suggesting that a quadratic model will be the better choice. So we will simply accept the default. We're going to jump over to the ANOVA. And here's the resulting model that we've identified. We have a significant model. We're able to do a lack of fit test. It's able to evaluate whether or not the model that we've chosen is a good representation of the data at large, and we want the lack of fit to not be statistically significant because we want the model to fit. So here we have a good indication that it's in a desirable direction. The fit statistics meet all of our criteria. Okay, adequate R squared and predicted R squared, adequate precision is above 4, so we're happy with that. So we'll go to the diagnostics. And here, let's just kind of take a look at something. We said we want to see the residuals follow that normal distribution. And I'm going to lasso this particular point and highlight it because that one just looks a little bit strange. If I go to the next chart, it remains highlighted, and that one is showing that on the residual versus predicted, it's not out of control. It's not outside the red limits, so that's not terribly concerning. If I look at the predicted versus actual, well, that data point does stand off the line a little bit. So let's say that we're a little bit nervous that that data point might be a little bit off for some reason. Now we're going to look at the influence plots on the bottom right. And I will look at two in particular, the Cook's distance, and probably even more importantly, the difference in fits, the diffits. Well, the difference in fits is telling me how much impact does that particular data point have on my model? You know, how different is the fit if I include or I exclude that data point? Well, that data point is within the blue line, so basically it's having no more impact than any other data point. And so we're going to reach the conclusion that even if that data point were to be a little bit off, we're not going to concern ourselves. Okay, and then we could look at the model graphics if we want to, and we can look at a 3D surface. I always like those because they're cool. And if we toggle the catalyst back and forth, we can see how much impact that has on the response surface itself. Okay, so there's a lot of moving parts that we're able to identify with this model. Let's move on to the second response, the activity. We need to go to fit summary. This one is a simple linear model is what's being suggested, so we will simply take that. When we look at ANOVA on that one, we look at the fit statistics, the predicted R-square of 9276, and we look at the model itself. This p-value for the temperature is quite a bit higher than the 0.05, and one could make the argument that that doesn't need to be in the model. Perhaps we could get rid of it. That's called model reduction. And what we're trying to do is if we do reduce the model and get rid of terms that don't need to be there, we're trying to look at the impact that it has on the adjusted and maybe even more particularly the predicted R-squared values. So if I go back in the model and I double click temperature to get rid of it, so it's no longer in the model, I actually marginally improve the predictive capabilities of this model. It's a better model by getting rid of a term. So we'll keep that. We'll go with that. Quick look at the diagnostics, and that looks pretty good. Now, the next thing we want to do is find the optimal conditions that maximize our impact for both the conversion as well as the activity. So I've come down under optimization, numerical optimization. I am going to come down to conversion and set a goal for that. The conversion we want to maximize. And we said we want to be at least 80%, but of course, if we can get to 100, that's better. So I'm going to set my limits from 80 to 100%, and this little picture on the bottom kind of shows how our goal is set up. Activity, well, we decided we want to target a value for that one of 63, but we're willing to accept anywhere from 60 to 66. So we have this little triangular shape pattern down here on the bottom. And then we hit solutions. And here would be the answer for that. So we have the time, the temperature, and the catalyst. That would deliver 91% on the conversion and pretty much hit the 63%. Just briefly, let me go back to the criteria just to show you a little feature. What if conversion was a whole lot more of an important goal than activity? Well, we can change the importance to, let's say, give that 5 stars, and maybe activity is really not that important at all, but we put that at 1 star. Now when we hit solutions, it will bias our results to give us a little bit higher conversion. I think we had 91 before, now we're up to 93.5. And instead of hitting right on 63, we're down to 64.4 or up to 64.4. Still within the range of acceptability, but we've biased our solution set to kind of give a little bit more attention to the conversion. Okay. So that is that example for response surface. Things to remember. RSM designs are useful when we have curvature or nonlinearity in our design space. The model terms include quadratic or even higher order terms in addition to the main effects and interaction terms. RSM designs will require more runs than the factorial designs. but we get more information. We can use the numerical and graphical optimization tools to find the optimal conditions to satisfy one or more criteria. Okay, so we had a peek at how to do that. All right, show of hands, are we still there? Excellent. Thank you. Okay. Now we're going to take a look at mixture designs and why they're a little bit different. So what makes a mixture? Well, I think we all kind of know what that's about, but in the end, let's kind of put it to words. The factors are ingredients of a formulation or a mixture. And the response is not really driven by the absolute quantity involved. It has to do with the proportions or ratios of the ingredients, not the absolute amount, okay? So that gives us a little bit different situation. And let's kind of take a look at if we try to use the factorial design where we let everything go from its low level to its high level, and we try to use the factorial to do a mixture, here's the kind of a problem we would have. We're making lemonade out of sugar, water, and lemons. In the bottom left, we do a 1-to-1 ratio, okay? 1 glass to 1 lemon. Go from low to high on the lemons, so now we'll go 2 lemons to 1 glass. And let's go up here. We have 1 lemon to 2 glasses of sugar water. And in the upper right, we have 2 to 2. Well, the problem we have is we haven't taken into consideration the overall constraint that the formulation needs to sum to a total. And the consequence of that is we have 2 experimental conditions that are actually the same. This one on the bottom left and the upper right are actually the same formulation. I just have more lemonade in the upper right. Won't impact the taste though. So if we use a standard factorial, we're going to get very confusing results because we haven't taken into consideration the built-in constraint. If we add a third factor, let's say we're doing lemonade with iced tea in it. In a factorial design, we're free to vary all 3 of our factors anywhere in this cube. However, in a mixture design, once we pick 2 of them, the third can be calculated by difference. So our design space is now a triangle. You can't operate within the full cube because of the constraint. Okay, so that poses a problem, and our software with the mixture designs accommodates that situation. Okay. So what we're going to do is we're going to work with a mixture and an amount experiment. So we're going to go right past just a pure mixture experiment, and we're going to go to an even more complicated one where we're going to work with mixtures, but then we're going to have a process factor called amount. For example, fertilizer, where the yield of a crop might be a function of both the proportions of the ingredients in the fertilizer and the absolute quantity used, right? You use a little fertilizer, it's not as good as maybe if you put more. Paint coverage, it's not only the proportion of the ingredients, but the thickness of the coating that you apply. And of course, medicine, right? The effectiveness is both a function of the proportions of the ingredients and the dosage that we're given. Okay, so mixture plus amount. So here's our situation. We're doing a pharmaceutical formulation. We're trying to create a timed-release ibuprofen tablet by putting a coating on it made from an emulsion. A latex coating. So what we have 3 ingredients, EA, MMA, and TEC to keep it simple, and they range in the values indicated. So that's the formulation. Then we have the total quantity of the latex coating that we will use in a lab coater, and we're going to either go from 15 to 25 mLs into this lab coater to give us different thicknesses. And what we want to look at is how much drug is dissolved after 1 hour and then after 12 hours. Okay, so a timed release tablet. So optimize the coating formulation and amount. We want to have 20% dissolved after 1 hour and 90% after 12 hours. So let's open up that design. All right. So here we're beginning this one. This goes all the way down the list into the custom designs optimal. And we have 3 components to the mixture, and we have 1 numeric factor. Okay, so we're going to let the computer create a design for us to evaluate that system. The total formulation will sum to 31%, and apparently we have a slack variable, or maybe it's water or something, that we're going to balance this out to 100%. But the part that we're evaluating is held constant at 31%, and it's each ingredient is in that range. Okay, so we accept that. Then we will put the coating variable in, and that's going to go from 15 to 25 mLs into the lab coater. We accept that. It will offer this this design. It's going to model a quadratic by quadratic, so quadratic for the mixture and quadratic for the process factors. And this will create a design of 28 runs. So we will simply accept the default in this case and move forward. As before, we will put our 2 responses in. We'll finish it. And we'll get our data. Okay, and now I need to do the analysis again. So what we're going to do is we're going to hit dissolve. We're going to go to fit summary. And now it has to pick the order of the model for each of the mixture and the process. Once again, we will accept the suggested quadratic by linear in this case. So we'll click on model. We're going to do quadratic by linear. Now, there's a little feature that I'm going to turn on, and it's beyond the scope of this 1-hour discussion to get too deeply into it, but I am going to let the software remove some of the model terms, and that's almost always necessary in these combined designs. I'm going to use something called AICC as the criterion and backward as a selection, and I'll hit start, and it'll choose to remove some terms, okay? So I'm going through that very quickly. I want you to know that it's there. But it's beyond the scope of what we have time to cover to get into it in great detail. Then when I hit ANOVA, I'm going to get a warning that the model is not hierarchical and it needs to add back some of those terms. So we're always going to say yes to that question and move ahead. Okay. So now we've created the most appropriate model. It is significant. The lack of fit is not significant. I have these terms included. And there's my fit statistics. It's all good. I will always take a quick peek at the diagnostics, and that looks satisfactory. Okay. Now we're going to do the same thing for the 12-hour. I will hit fit summary. It likes quadratic by linear, but on the side it's doing this other test to see if something called a KCV model fits, and in this case it likes that even better. So we will accept that as the default, the KCV. And we are going to do the auto select again to get rid of terms that don't belong there. It found a couple to remove, and that actually improves the predictive capability of our model when we do that. Okay, and we look at the diagnostics. All right, so we've designed our experiment, we've conducted the experiment, we've analyzed both of our responses. Now we can do the numeric optimization. And we can come in and put our targets in. So for dissolve after 1 hour, we are going to target that. And we wanted 20% on that. And the range we'll accept is anywhere from 10 to 30. So we have a little triangular pattern down here again. And for 12-hour, we want to target 90%, and we will accept anywhere from 80 to 100. And that's what that one looks like. And then we hit the solutions. And here's what we achieved. If we use that formulation, right, with the EA at 13.9, the MMA at 13, etc. If we use that formulation and we charge the lab coater with 18 mLs of coating, we expect to have 24.8 dissolved after 1 hour, and 87.4, which was each of those is inside the criteria that we set for ourselves. Okay, so that is what that one looks like. So things to remember: mixtures have a built-in constraint. The formulation must sum to a total, and our design needs to accommodate that particular aspect of mixture designs. And because of the constraint, special approaches are needed to build the DOEs for mixture and model the results. And design expert can create custom optimal designs that combine mixture components and process factors, as we did in this case, which are fairly sophisticated designs. So the overall summary then is DOE is a planned multi-factor approach to efficiently and effectively determine cause and effect relationships. You know, it's better than one factor at a time in that you can get the interaction between variables. Okay, so this is a pretty good tool. DOE statistics provide power and credibility to the conclusions. We have between the power and the statistics, the standard deviation, you know, there's a lot of information that's brought forward so that when we say something is significant or we make predictions, that we have some statistics to back that up. Design expert software specializes in DOE. It provides a wide variety of design types. We've tried to show you as many as possible in a few minutes. Obviously, there's a lot of detail to know and understand to effectively use all of those. So what I would ask you to do is to think about the kinds of designs that you would most likely do. Maybe it's mixture, maybe it's formulation, maybe it's process work, maybe you're doing screening designs, and then maybe envision how to do a little bit more of a deep dive in those areas. And let's talk about some ways to get that done. First of all, since we're all at home these days, or a lot of us are, we have some distance learning opportunities that have just been created. So there's a boot camp for experimenters. That's a guided self-paced learning for Factorial design basics, right? So Factorial designs, that first case study that we showed, if that's your area of interest, here's a place where you can sign up and get a little bit further down that road. We also have modern DOE for process optimization. So this is kind of a light version of what I'll call the full in-person training class, but this one will get into Factorial designs and also response surface methods. Okay, so a little bit more complete than the first one. Hopefully someday in-person training will become a thing once again, and then we can give you the full modern DOE for process optimization. That's a 3-day course, and that would cover Factorial designs as well as response surface methods. We also have a 2-day course for mixtures, which includes mixture designs and then the combined designs where you can have mixture plus process variables, much like the one I just went through. And there's more options available for training at staties.com, so feel free to take a peek at that. There are books written by folks at Staties. These are not heavy reads. These are kind of a lighthearted, fun-spirited, but very helpful books on the basics of DOE simplified, RSM, and now the formulation book as of the last couple of years is now out there. Okay, so these are very helpful as well. There are industry-specific success stories out there that you can find in our website, so feel free to browse those to get ideas for how this is used. You can also go out to YouTube and find Statistics Made Easy videos. They're out there. There's white papers and other publications at our website. In the software itself, I could have pointed out, but there's a little light bulb that gives you context-sensitive help screens. So if you're on a screen and you want to know what to do with it, that little light bulb will take you to some help to walk you through it. We also invite you to email stathelp@staties.com for answers on any question you may have. We're here to help. We're happy to do so. Also, if you're interested in receiving some practice files for the case studies I went through today, please email stathelp@staties.com and we'll send you the practice files to follow along or practice on your own, okay, to see how those were done. That's it. So we encourage you to make the most from every experiment. We hopefully have convinced you that the statistical capabilities within Staties Design Expert is pretty powerful. and yet fairly simple to use. I know we went through it quickly, but as you do a couple of those on your own, I think you'll find that it's actually fairly simple to use. With that, I thank you for attending. We look forward to seeing you in additional training, hopefully at some point in the future. And in the meantime, I encourage you to stay safe, and we'll talk to you again. Thank you very much for listening.